Alright folks, welcome back to another Math Notes. We're going to look at probability models today. This is section 3.1.4. So when we're talking about probability models, we're talking about ways that we can use pictures to visualize the probability of events occurring. So let's take a look at this scenario. We're going to look at two main ways of doing that. So when considering two or more probabilistic situations with outcomes that are not all equally likely, a tree diagram or area model can be used to calculate probabilities of compound events. Okay? So when more than one thing is happening and those things are independent. So we have this scenario. Suppose you spin the two spinners shown at the right with the probabilities shown in the table below. So let's imagine that we have a little arrow on this spinner, and I'm actually going to redraw that. A little arrow on that spinner, and we come along and we spin the spinner, spin, 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 and it lands on an A. And then we have another spinner here, and it can spin, 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 and land on its own thing as well. Well, not all of those are equally likely, right? Because it looks like, if we think about it, this I on the left-hand spinner number one is taking up 50% of the spinner, or 1/2 of the spinner. The region U is taking up 60 degrees of a 360-degree circle, so its probability is 60 out of 360, which we can reduce to 1/6. And region A is taking up 120 degrees. We know that because 60 plus 120 is 180. So its probability is 120 out of 360, which reduces to 2/6, or 1/3. Over in spinner number two, which we will redo in blue, we have area T, which is a 90-degree angle, so we know that its probability is 90 out of 360. There's 360 degrees in a circle. Region T is taking up 90 degrees of those, so that's 1/4. And region F must be taking up the rest, which would be 3/4. So we've gone and put all of these into what we call a probability area model over here on the left. So let's go back to our color coding. I has 1/2 chance, A has 1/3 chance, U has 1/6 chance. I want you guys all to be writing this down as we go. You might need to pause the video. T is 1/4, F is 3/4. And we're going to find the probability of various combinations occurring the same way we did with our with the other times that we use these area models, right? So when we're multiplying binomials or that sort of thing. We're going to stick with the base times height equals the area concept. So for an I and a T to occur, we're going to say 1/2 times 1/4. So our I is 1/2 times the 1/4. We multiply 1 times 1, we get 1. 2 times 4 gives us 8. So there's a 1/8 chance of getting an I and then a T. For AT, we're going to similarly multiply 1/3 times 1/4, which gives us 1/12. So there's a 1 in 12 chance that we would get that combination. U and T would be 1/6 times 1/4, or 1/24. Remember, when you multiply fractions, you multiply the two top numbers. So 1 times 1 is 1, and 6 times 4 is 24. IF would be 1/2 times 3/4, which would be 3/8. AF, 1/3 times 3/4, which reduces to 3/4. Initially you would get 3/12 and need to reduce that to 1/4. UF would be 1/2 from the U times 3/4 from the F. Multiply across, we get 3 over, oh, I'm sorry, it's 1/6 from the U, 3/4 from the F, so that gives us 3/24, and that reduces to 1/8. So now that we multiply that all out, we could say, if there was a problem that asked, what are the chances of rolling a U and then an F, that would be 1/8. All right, so area models are great if there's exactly 2 probabilistic situations, because you have to put one of those on the base and one of them on the height of your rectangle. Once you get more than that, you get into 3 dimensions. It's tricky to draw and think about. Okay? This situation is represented by a square with an area of 1, so that the areas of the parts are the probabilities of the different events that occur. The outcomes of one probabilistic situation are across the top of the table, and the others are down on the left. And then they walk you through the example that I did here. UT is 1/6 times 1/4 or 1/24. Another way to model this same information would be to use a tree diagram. Tree diagrams look like this. Tree diagrams can be used when you have 2 or more probabilistic situations. So once you have more than 2, you probably want to go to a tree diagram. In this case, we're still just modeling the 2 spinners. So we can think about it like this. We have our first spinner here. Let me make sure that these colors match. Yes, they do. We have our first spinner here, where we can get an I, an A, or a U, and we have our second spinner in each of the branches. So we have TF there, and TF. So if I wanted to figure out what were the odds of getting, say, AT, what I'm actually going to end up looking at is this path right here. So going back to the spinners, we already calculated it. The probability of getting an A was 1/3. The probability of getting a T was 1/4. So we multiply 1/3 times 1/4, and we get 1/12. If you want to go down the other branches, the I had a 1/2 chance of occurring. The U had a 1/6 chance of occurring. So I put the probabilities for those first spinners on the first branches, and the probabilities for the second spinner on these branches. So 1/4, 3/4, 1/4, 3/4, 1/4. Come on, undo. 1/4, 3/4. Some of you might be wondering why we've repeated the second spinner 3 times. Well, that's because the branches are independent. So we're going to go down branch I. Now that we know we've gotten an I, we could then get a T or an F. Alternatively, we could get an A on the first spinner and then still get a T or an F on the second spinner. Or we could get a U on the first spinner and then a T or an F on the second spinner. And we would calculate the probabilities for each of these by going down the branch that's associated with that combination. So if I wanted to know, say, UT, I find the branch with UT, UT, and I multiply 1/6 times 1/4, and I get 1/24. All right, guys, write that down, process that for a little bit. And then I want you to try, see if you can come up with what you think an area model would look like for flipping a coin and rolling a dice. So the outcomes of flipping a coin, you could either get an H or a T, head or tail. Rolling a dice, you could either get a 1, a 2, a 3, a 4, a 5, or a 6. What do you think those area models might look like? Try to draw one up, draw a tree diagram if you can. So create an area model and tree diagram for this scenario. And we'll talk about it in class